So I want to do one more optimization example. I'm planning for this to be the last example because we've gone through a lot of them by now. But this one specific is specific to statistics. So I've kind of mentioned where this is used in statistics. I've alluded to like the maximum likelihood estimator. It's also used in like finding the coefficients of the regression equation, for example. Um, But I want to go through, okay, well, how do we actually put that into practice? So we're going to brush over a little bit of the details that you'll get more in like statistical theory class. Um, but I just kind of want to show how this is used so that you can see it in practice. And if you've already done some statistics, maybe this will help it click a little bit more if it hasn't already. And if not, you can kind of see what we're building towards by looking at these partial derivatives and stuff like that. All right, so what we do here is we say, okay, let x1, x2 to xn be a random sample from a normal distribution with unknown mean, mu, and variance, okay, sigma squared. Okay, and we want to find the MLE of mu and sigma squared. Okay, not sigma, sigma squared, which is an important distinction here. So the MLE, so you've seen this on homework problems a little bit, but basically you come up with the likelihood function and then you maximize it, right? So it's the maximum likelihood estimator, okay? So first thing we need to do is come up with the likelihood function. That's just normally given to you, but in general, the likelihood function for some xi, okay, given, sometimes you write it with theta, but I'll write it with mu and sigma squared here. I don't think that books are very consistent about the way that they write this. Technically, likelihood functions, though, should be written the opposite way. So it's kind of a subtle distinction, which, again, is more of a topic for a statistical theory class than this class. But so the way we would read this is that this is a function of mu and sigma squared given some observation xi. So this is the likelihood function is a function of the parameters given the data, and a probability distribution function is a function of the data given the parameters, but they're the same function. It's just different in what is fixed versus what is a variable. Okay, so anyway, so this would be 1 over just sigma root 2 pi, and then e to the, which we can write as the exponential function of negative x minus mu squared over sigma squared. Okay, 2 sigma squared rather. So this is for one xi. We, to find the likelihood estimator for all of it, all we do is multiply them together, or likelihood function, I should say. Given all of the data, then would be the product of all of these, and this should have been an xi. So what does that look like at the end? Well, that's going to look like 1 over sigma to the n, because we're going to have 1 over sigma times 1 over sigma times 1 over sigma n times. You can add the exponents together there. Root 2 pi to the n by the same logic there. And then the exponential function of 1 over 2 sigma squared, and then the sum of I equals 1 to n of xi minus mu squared. Okay. So this part I think should be clear if you just like write out a couple of the terms. Basically, this is an exponent, so when you multiply them together, it's going to turn into the sum, right? So you have x1 plus x2 plus x3, and this is what you end up getting here. Okay. So as you've also seen on some homework problems, it's much easier to work with the log likelihood function. So we take the log of this. Sometimes it's written just as like little l of this function. So I'll write it like that here. But what this is the log of this stuff here. So the log lets us break up the product into a sum. So, and then also pull the exponents out front. So this is going to be negative n of the log of sigma minus n over 2 log of 2 pi. And when we say log here, we mean natural log, but it doesn't really matter what the base is. Okay. And then this just goes away, and then we have minus, and these twos could have canceled out, by the way, minus the sum of I equals 1 to n of xi minus mu squared over sigma squared. Okay, so this is the function we're working with. On a homework, you already found this for just one observation, right? So this should look a little bit familiar. Now we're just doing it for all the observations. So now what we would do to maximize this function is, there's a lot of variables here, but there's really only two variables. There's a bunch of x's, there's n's, but we would consider those to be known, right? If we were actually looking at real data, we would know what the observations are, and we would know how many there are, which is what n is. We just don't know what mu and sigma are in this case. So we're going to take the partial derivative of L with respect to mu. There is no mu in this term, so that's 0. No mu in this term, so that's 0. There is a mu in this term. So it's going to be negative 2 I equals 1 to n xi minus mu times a negative 1. So that'll cancel out here. All over, this should be 2 sigma squared. Did I cancel something out? That shouldn't have. This one, I don't know why I had this 2 in the numerator. Right, it should have just been like that. Yeah, I think I just wrote it twice on accident. So yeah, that wouldn't have canceled out, but now they cancel out. Okay, so we're gonna set this equal to 0. So multiply both sides by sigma squared if you like. So you have I equals 1 to n of xi, and then if we break up the sum, we're summing mu n times. So that's going to be minus n mu, right? Mu plus mu n times is going to be n times mu. Okay, equals 0. So this will imply that mu is equal to I equals 1 to n of xi over n. And then hopefully that looks familiar to you. That's the sample mean, right? So the maximum likelihood estimate of the population mean is the sample mean. Okay. So maximum likelihood estimation is, what it sounds like. It's like, what is the most likely value for the population mean? Well, the most likely value based on the data that we've just seen, right? So the most likely value based on that data would be the sample mean, right? So now we'll go ahead and do the partial derivative with respect to sigma squared, okay, so you know, we do need to be a little bit careful about that. I think to make this easier, we want to write this as sigma squared. So what I'm going to do is I'm going to put a squared in here and put a 2 down here. Okay, so this way, you know, those two things just cancel each other out. So like we could bring, this would be like 1/2. We could bring that up here and then it would just be sigma. So that's why we can put the squared back in here if we also put the 2 here, because again, they would cancel each other out. So we got to be a little bit careful here when taking the derivative, because this is with respect to sigma squared, not with respect to sigma. That's why some people like to write these as like theta 1 and theta 2 or something. So it's a little bit clearer. But I think we can just power through, right? So remembering the thing is sigma squared, so we're not going to use like the chain rule there. So the derivative of this then would be 1 over sigma squared times the negative n over 2 out front. Okay. There's no sigma in this. There is a sigma on the bottom here. So this is like sigma squared to the negative 1, right? So we would bring that negative 1 out in front, which will cancel that one. And then we'd have sigma squared to the negative 2 on the bottom. So sigma to the 4th on the bottom. Or you could just write sigma squared squared if you want to keep it in that form. Okay. So we're going to set that equal to 0. And then you can go ahead, you can multiply everything by sigma sigma to the 4th, I guess. All right, so this will be negative n sigma squared over 2. This sigma to the 4th will cancel. And I'll just break this up now. Xi minus n mu equals 0. Okay. Actually, can't do that because I forgot to write the squared here. Right, there should still be a squared on there. Okay. So that's what it will look like. All right, so now we can solve this for sigma squared. So that's going to be equal to, we'll bring this to that side and then we'll divide by that. So it'll be negated there, or the two negatives will cancel out rather. So I equals 1 to n of xi minus mu squared over n. And then we have a 2 right here. And I'm realizing I also forgot the 2. I just copied, yeah, I copied this down wrong, right? Because I originally canceled that 2. I forgot to change it right here, and then I recopied it, so I just keep forgetting it. So there should be a 2. We can keep that there. So there should be a 2 here. So in the beginning, you could have just multiplied across by 2 sigma to the 4th and just canceled out all of the 2s. So we don't have to worry about this 2. Okay. All stemming from that same mistake of canceling the 2 too early. Okay, so we see this is the estimate then for sigma squared, which should look pretty familiar. This is the formula for the population mean, right? This one right here, when we write it like this is when we typically put the hat over it. So we say this is an estimate for the population mean, which is the sample mean. So then we can put the hat over this, which would put the hat over that parameter as well. And we can go ahead and throw in the sample mean, since we already found that that's what that is. Okay. So maybe a little surprisingly, the sample standard deviation is not the MLE for the population standard deviation, right? Because you don't have the n-1 in the denominator. So it's a little bit different. The reason we put the n-1 in there is to make it an unbiased estimator. So in this case, the MLE does not have the requirement of being unbiased. So that's why it doesn't show up here. Instead, this is what we sometimes would call the uncorrected sample variance. So now you might also be wondering, like, we didn't actually show that it's a maximum. We just found the critical points, essentially. We didn't do anything about showing it's a maximum. So we could do that too. It is quite a bit more complicated here just because the derivatives are more complicated. Namely, I think the most complicated part is the derivative of the sigma squared, the second derivative of sigma squared here. And just because you have a lot of sigmas and n's floating around, and then determining the sign can be a little bit tricky. Not impossible. You could give it a try if you'd like. But yeah, it's definitely a little bit more involved.